machine learning. So let's look at the next question, which is about reference models. Let's read the question first. A simple reference model for comparison is called a dash model. The answer here is baseline. Before training complex models, establish a baseline, a simple reference model to compare against. Let's look. Let's look why baseline matters. Because it sets a minimum performance threshold. Because it tells you if your complex model is actually better. Because it helps identify if improvement is significant, and also provides sanity check on your approach. Uh, let's look at some of the examples of baseline. Predicting average, it predicts average, always predict the mean value. Predicting mode, always predict the most common class. Simple rule-based model, easy decision rules, and naive bias. Simple probabilistic model. Let's see how to use a baseline. Train first you need to train a baseline model, then you need to train your complex model, then you need to compare performance, and lastly, if complex model isn't significantly better, question your approach. Yes, the beginners can make common mistakes to complex models without establishing baseline first. This makes it impossible to know if improvement is clear. Let's look at the next question, which is about data properties. Let's read the question first. Independent, unchanging data samples are described as test data. The answer here is independent. So the assumption of independent data is fundamental to most machine learning algorithms. What does independence mean here? It means that each data sample doesn't influence others. Observations are randomly sampled, no correlation between samples. Let's look why it matters. It matters because most algorithms assume independence. Violations can lead to biased results, and it also affects model evaluation validity. Let's look at some of the examples of non-independent data. Time series. Today's stock price depends on yesterday's. Also, pattern data from same hospital, similar patients cluster, and sequential manufacturing data. When independence is violated, let's see what happens. Standard cross validation may be inappropriate, need time aware validation strategies, and results may be overly optimistic. Let's look at the next question, which is about model initialization. Let's read the question first. Parameters tuned before training a model are called dash. The answer here is hyperparameters. Uh, there's an important distinction between parameters and hyperparameters in machine learning. Let's see what are parameters. Their values are learned from data during training. They're determined by the algorithm. Examples, weights in neural networks, coefficients in linear regression. Hyperparameters. They are the settings you set before training. Controls the learning process. Examples are learning rate, free depth, number of clusters. And here example of the algorithm is linear regression. Let's look at the next question then. This question is about model evaluation. Let's read the question first. Comparing two versions statistically, which one performs better is dash testing. The answer is the answer here is A/B testing. Comparative testing is crucial for model development and improvement. Let's see what it includes. Train two or more models, evaluation on same test set, compare performance metrics, determine which one is better. Let's see why it's important. Shows if one approaches are actually better, prevent false improvements from random variation, guides model selection decisions, ensure scientific rigor. Let's see the next question. Question 20. Features scaling matrix. It's about performance gap. Normalization typically rescales numeric features to the range, to the dash range. The answer is here is 0, 1. The normalization is the process of scaling features to a standard range, typically 1. Why normalize? Because it equalizes feature importance, because it speeds up training, it improves algorithm performance, it prevents features with large values from dominating. So for using normalization, we should also know when to use normalization. Because we use normalization when distance-based algorithms KNN, K-means, SVM are used. We use normalization for neural networks and for algorithms sensitive to feature magnitude. Let's see the next question then. The question is about train test step. Let's see the question. The difference between train and test performance measures dash. The answer is generalization. Let's look at generalization. Generalization is the ability of a model to perform well on unseen data, the ultimate goal of machine learning. Uh, Let's see why it matters. Real value comes from predicting unseen data. High training accuracy but low test accuracy is useless. Goal is to minimize generalization error. Ways to improve generalization are regularization, more training data, simpler models, cross validation, ensemble methods. Let's see the next question then. The next question is about sampling bias. Let's read the question. Bias sampling in data collection can cause test bias. The answer here is selection. Let's see selection. Selection bias occurs when your training data doesn't accurately represent the real world population you want to predict on. How selection bias happens? Let's look. Non-random sampling, excluding certain groups, self-selection, voluntary participation, data selection errors, historical imbalance. Let's see the consequences of sampling bias. Model performs well in training but fails in reality. Predictions are symmetrically biased, unfair to underrepresented groups, regularity and ethical issues. Let's see the next question. Here we the questions are over, and we have completed the part B. Let's see some of the key ML concept summary. So we covered feature engineering, transforming raw data into predictive features, regression versus classification, choosing the right problem type, overfitting and regularization, the more challenges in model development, ensemble methods combining models for better predictions, baseline models, and independent set parameters, normalization, generalization, selection bias. Uh, these 12 concepts from the foundation of applied machine learning. So this is the end to our video, and this was the section B of internal test paper 2. In the next video, we'll discuss section 3 of my internal test paper 2. Thank you for watching the video.